started with adiabatic process and completed various equations for that. Now in today's session, we are going to see numerical based on adiabatic process, and also we are going to start polytropic process. This is Faizan Kagdi and I welcome you all to our lecture series of basic mechanical engineering. So let's begin with our first topic, that is numerical. We are going to see numerical based on adiabatic process. Okay, so question is displayed on the screen. Determine work done in compressing 1 kg of air from a volume of 0.15 meter cube at a pressure of 1 bar to a final volume of 0.05 meter cube when compression is first according to isothermal process and second according to adiabatic process. We need to take adiabatic index gamma is equal to 1.4, and also it is given you need to comment on your answer. That is basically it means that we need to conclude that in which process work done for compression will be minimum. That process, in whatever process in which work done is minimum, will be preferred. Okay, that is whether isothermal or adiabatic. So first of all, writing data for this question. So in a data it is written mass is given for air, that is 1 kg. Initial volume V1 is given, that is 0.15 meter cube. Initial pressure P1 is given, that is 1 bar. Final volume after compression is given, V2 is equal to 0.05 meter cube. Okay, and gamma is written, that is 1.4. We need to determine work output. So considering case 1, that is isothermal process. Now what is an equation to determine work done for an isothermal process? So we would say that W is equal to P1 V1 ln V2 by V1 or log V2 by V1 to the base E. Now first of all, you need to see whether the requirement of formula is satisfied or not. So we would say that P1 is given in a data, V1 is also given, and V2 is also mentioned in the data. So directly we need to substitute all the values and we can determine work done for an isothermal process. So it is written that W is equal to 1 into 10 raised to 2, that is I have converted pressure which is given in bar into kilopascal. So 1 bar is equal to 10 raised to 2 kilopascal. So 1 into 10 raised to 2 into 0.15 into log V2 by V1, which means log 0.05 upon 0.15. So the final answer of work done is minus 16.47 kilojoule. Now negative sign indicates that work is done on the system, which means compression of air has been taken place. So this is our first answer. Now let's consider case 2, that is for adiabatic process. Now what is an equation for work output or in an adiabatic process? So we would say that W is equal to P1 V1 minus P2 V2 upon gamma minus 1. Now our next task is to see whether the requirement of formula is satisfied or not. So we would say that P1 is given, V1 is also given, and V2 is also given, and gamma is given 1.4, but P2, that is final pressure, is unknown. So our first target for determining work done will be to determine final pressure P2. Now think about it, that how we can do that. So we would say we know the law of adiabatic process, that is a relationship between pressure and volume we know. P1 V1 raised to gamma is equal to P2 V2 raised to gamma. By using this equation, we would say the unknown final pressure P2 can be determined. So I have mentioned it, as you can see on your screen. P2 is equal to P1 into V1 by V2 raised to gamma. After substituting all the values, we can get P2, that is final pressure, is equal to 4.65 into 10 raised to 2 kilopascal, and even you can write final pressure P2 in bar, that is equal to 4.65 bar. Okay, now whenever we are going to find out work done, so remember that the work done is required in kilojoule. Always keep this in mind. It is required in kilojoule, so we need to keep corresponding pressure in kilopascal. So we are going to substitute all the values in our formula of work done in adiabatic process. So it is equal to 1 into 10 raised to 2, that is initial pressure P1, into 0.15, that is volume V1, minus 4.65 into 10 raised to 2 into 0.05 upon gamma minus 1, that is 1.4 minus 1, which is equal to 0.4. So final answer of work done we get is equal to minus 20.62 kilojoule. Now compare both the answers of work done, that is from case 1 and case 2. So in case 1 from isothermal process, work done for compression is minus 16 kilojoule, and in case of adiabatic process we would say it is near about minus 20 kilojoule. So comparing both, we can say that work done for compression is less in isothermal process compared to adiabatic process. So which process is preferred for compression? So whichever process in which work input is lesser is preferred for compression. So we can conclude that work required for compression is less during isothermal process compared to adiabatic process. So isothermal process is preferred for compression. So this is our final answer. Okay, now let's begin with our next topic, that is polytopic process. So polytopic process, as the name itself suggests, that poly means multiple process. So we have seen several processes, that is constant pressure process, constant volume process, isothermal process and adiabatic process, right? So after seeing all this process, it has been concluded that let's form a generalized process in which all this process can be covered. So that generalized process which was defined afterwards was called as a polytopic process, which will cover all our processes. So we would say it is a generalized process which can cover multiple processes for a specific value of a polytopic index n. For example, in case of our adiabatic process, there was an index called adiabatic index, that is gamma. So for this particular process, we have considered that let's say this process also has an index that is called a polytopic index small n. So the value of this index can vary from minus infinity to infinity, but for calculation purpose, we will consider it from 1 to 1.7. So this process is represented by this following expression, which is given on your screen, that is Pb raised to n is equal to constant. Now how we can say that this is a generalized process? How it can cover all the previous process? So we would say that by placing a specific value of a polytopic index n, we can obtain various processes such as constant pressure process, constant temperature process, adiabatic process and constant volume process. So let's see how we can achieve that. So in case 1, you can see that I have taken polytopic index n is equal to 0. So when we place this n is equal to 0 in our polytopic process equation, so what we will get? So we would say Pv raised to 0 is equal to C, which means v raised to 0, v to the power 0 will be always equal to 1, which means we get P is equal to C, indicating pressure is remaining constant when we place n is equal to 0. So this polytopic process will now be reduced to a constant pressure process, provided if we take n is equal to 0. Now in case 2, as you can see, I have taken n is equal to 1. We are going to take different values of n. Okay, so in the next case, I have taken n is equal to 1. Placing this value in our expression of polytopic process, we can get Pv raised to 1 is equal to C, which means Pv is equal to C. So we can say that this polytopic process has been now become constant temperature process. Okay, so I hope that you are clear up till here. That is, polytopic means multiple process can be covered. Now let's see our next case. That is case number 3, in which I am going to take polytopic index small n is equal to gamma. So if small n is equal to gamma, so the equation will become Pb raised to gamma is equal to constant. So we can say the process, that is polytopic process, has now become adiabatic process. Okay, now in case 4, you can see that I have taken n is equal to infinity. So when n is equal to infinity is taken, so the process is going to reduce to constant volume process. Now how? So you can see I have written Pv raised to infinity is equal to constant. Now remember that our target is to do a power of volume, that is V is equal to 1. So for this I am going to divide the power on both the sides by infinity. So I have written P raised to 1 by infinity into V. Now infinity upon infinity we are going to take 1. Don't relate it with our mathematics, that is L hospital rule. It is over here, just we are going to make a power of volume equals to 1, so I have divided by infinity. So the volume power becomes 1 is equal to C raised to 1 upon infinity. Now we know that 1 upon infinity will be equal to 0. So we can say that in the next step it will be P raised to 0 into V1 is equal to C raised to 0. Now it is again equal to constant, so it will be equal to 1. So directly we can write that P is equal to 1, which means P is equal to C. So the process has been reduced to constant volume process. Now in this process also we need to perform our 5 most important tasks. That is, we need to determine work done is how much, change in internal energy is how much, change in enthalpy is how much, then how much is the heat transfer during this process, and pressure, volume and temperature relationship. So while determining this 5 things, we can say that the equation for this process, that is polytropic process and adiabatic process, is going to remain same as we have derived the equations for our adiabatic process. In this case, just we need to replace the value of gamma, that is adiabatic index, by our polytropic index small n, right? So equation we can get same as an adiabatic process. So I have mentioned over here. So the main difference in the equation of adiabatic process is that if we replace gamma by n, we can get a relations for a polytropic process. So I have mentioned that first work done, we know the formula for that. W is equal to P dV, pressure into changing volume. So further we can write W is equal to integration from state 1 to state 2 P dV, right? Now if you remember that pressure and volume both were variables, so we were placing a value of pressure in terms of volume. So in this case we can place P is equal to C upon V raised to n. After integrating and performing all the tasks, what we are going to get? So we would say we are going to get a formula for work output, which is equal to P1 V1 minus P2 V2 upon n minus 1. Similar to our adiabatic process. In adiabatic process, we were getting equation P1 V1 minus P2 V2 upon gamma minus 1. Right. So we can directly replace the value of gamma in our adiabatic process equation by this polytropic index small n. Okay, now our next task is to determine change in internal energy delta U. So again, the formula of delta is going to remain same, that is NCV T2 minus T1. Next task is to determine heat transfer for this process. So we know according to first law of thermodynamics, that is Q is equal to delta U plus W. So we can directly apply this equation by determining work done and delta U in order to determine the answer of heat transfer. Okay, now next task is to find out change in enthalpy. So what is the formula of change in enthalpy? So up till now we have done this task. So I hope that you are clear with the formula how we can determine change in enthalpy. That is delta is equal to H2 minus H1. After determining all and substituting all the values, what we are going to get the equation of delta H, that will be equal to NCP T2 minus T1. So up till here we have seen 4 tasks. That is work done is how much for a polytropic process, then delta U is how much, change in internal energy, then heat transfer is how much, and fourth one is delta H is how much. Now last we need to see the relationship among pressure, volume and temperature for this polytropic process. So we can say that the equations are going to remain same as an adiabatic process, just we are going to replace the value of gamma by our polytropic index n. So as you can see on the screen, I have written P1 V1 raised to n is equal to P2 V2 raised to n, which is a relationship between pressure and volume for this process. Second equation, to determine our PV relation and TP relation, we need to also use a combined gas equation, that is P1 V1 by T1 is equal to P2 V2 by T2. Now in the next step, I have converted our equation number 2 in form of T2 by T1, so we can write it as T2 by T1 is equal to P2 V2 upon P1 V1. Now next step is to substitute the value of P2 by P1 from our equation number 1. So observe carefully, we can write that P2 by P1 is equal to V1 by V2 raised to n. Right, so I have written V1 by V2 raised to n into V2 by V1. Now further we are going to arrange this volume ratio in form of V1 by V2. So we can write in the next step T2 by T1 is equal to V1 by V2 raised to n minus 1. Okay, so this is our TB relation. Remember this equation, TV relation, temperature and volume relation. Now further we need to determine TP relation. So what I am going to do, I am going to substitute a value of V1 by V2 in this equation from our equation number 1. So observe carefully. V1 by V2 is equal to P2 by P1 raised to 1 by n. Right. So substituting P2 by P1 raised to 1 by n in our last equation, that is of V1 by V2. So we are going to get a final equation of TP relation, that is T2 by T1 is equal to P2 by P1 raised to n minus 1 upon n. Okay guys, so I hope that you are clear with the numerical of adiabatic process and our polytropic process and the equations for this particular process. So in today's session we are keeping up till here, and we will continue in our next session with the numerical of this polytropic process. Till then, stay tuned and thank you all.